So um, today's lecture is going to be on integer programming, and then you can consult our textbook on chapter 6, and then you can also look at some materials from MIT OpenCourseWare, and these courses also available on the internet. So just a little bit of introduction. So we have been looking at linear programming problems when decision variables are assumed to be real non-negative numbers. But in fact, we have explored what happens when the decision variables are integers already. So this is just a little bit of going into details. So um, integer programming problem is when we have decision variables being integer, and we call them integer linear programming problem. And ILPs occur frequently. Examples include scheduling workers and manufacturing decisions. And integer variables also allow us to build more accurate models for a number of common business problems that we will take a look. So let's look at the concept of feasible areas and bounds. So suppose this is the blue area is a feasible area, and then we have corner points 1, 2, 3, 4. And so when decision variables are allowed to be real numbers, real non-negative numbers, so the feasible areas are all these areas. But then when we apply the constraint that decision variables must be integers, so the feasible solutions are only the ones on the grid, like here 0, 0, 1, 0, 2, 0, and so on. So the feasible integer solutions are just all these dots. Okay. So suppose we consider the objective function of an LP problem. That is when there's no integrality constraint. And suppose we also look at the objective function when we apply the integrality constraint for the same problems. Okay, so there's a relationship between these two. So note that for the maximization problem, so by maximization, we mean bigger is better. So which one do you think is true? So which one would you think is doing better, the LP or the IP? So you can see that the feasible solutions of integer problems is a subset of the linear programming problems. So we always do better for the LP. So by so when we do better for the LP means that the objective function for the LP would be higher for the IP, at least better than the IP. So the answer is this one. And then for the minimization problem, so smaller is better. Smaller. So if this is the case, then the LP is doing better. So the objective function of the LP is less than or equal to the objective function of the IP. Okay. So note that the objective function of the linear programming is always better than or equal to better than or equal to the objective function of the IP. The reason being that the feasible, the set of feasible solution of linear programming is a subset of that of IP. In other words, we have more choices for the linear programming problem, so that's why we always do better than the IP. Okay, and we can solve the LP relaxation problem instead of an IP. In the old days, when computing power is limited, solving the integer programming problem is much harder than an LP. So instead of directly solving an LP, directly solving the integer problem, we just solve the LP problem, as assuming that assume no integrity constraint. So this is what we mean by LP relaxation problem. We assume no integrity constraint. And then after we solve the LP problem, then we sometimes round. Round means round up or round down or round to the nearest integers. So the problems with rounding is that the rounded solution may be infeasible. It might fall off the feasible area, and then the rounded solution might not be optimal, so it may be suboptimal. So with better heuristic and higher computing powers, so now instead of solving LP relaxation problem, we go directly to the IP, at least for the problems that we are looking at in this class. So the first problem for that illustrates the integrality constraint is the subset selection problems. So often models are based on selecting a subset of elements. For example, in the knapsack problem, one wants to select a subset of items to put into a knapsack, so as to maximize the value while not going over a specified weight. Or one wants to select a subset of potential products in which to invest, or one has a set of different integers and one wants to select a subset that sums to a value k. In this case, it is typical for the integer variables to be as follows. So we define xi as either 0 or 1. Is 0 when it's not selected and is 1 if it's selected. Okay, so this problem is called a knapsack problem. Knapsack means a bag. So we want to select some items to put in a bag. So in this example, there are 6 items to select from, and then we want to choose the items whose cost sums to at most 14. So the budget is 14, and we want to maximize the utility. So this is our data. So we have to find the objective function. So suppose the cost is CI, cost of item I is CI, and then the value is vi. Okay, it's vi. And then I think I do a small vi. Okay, and then we want to define the objective function. So the objective function is to maximize utility. So we maximize total utility. So we can easily say, remember that we define this decision variables to be xi, and it's 1 if element I is selected and 0 otherwise. So we can maximize total utility as 16x1 plus 22x2 and so on until the last term, 19x6. Or we can write it in a summation as a sum from I equal to 1 to 6 of vi xi. Okay, so we max total utility. So it's essentially v1 x1 plus v2 x2 and so on until the last term. And the constraint is that we have the budget of 14. Okay, so the constraint is that the cost, so we can say 5x1 plus 7x2 plus and so on until the last term, 6x6 cannot be greater than 14. Right? Yeah. And then we also have the binary constraint that xi can be either 0, 1, xi in the set of 0 or 1. Okay, so we have a small problem of one constraint and one object. Oh, actually two constraints. So this is called binary constraint. And then so we're going to, actually this problem is not so big. You can actually might be able to do it by hands, but we're going to do it on Excel. Okay, so this is the, so you open up the IP blank file, and then you're going to see the file called subset. Okay, so we are going to first, so this is the data that we have. So this is the decision variables. So these are decision variable. And then, so we're going to maximize total utility. So we can just do some product of the value. So it's like V1 X1 plus V2 X2 and so on. And then we want to find the total cost. So some product of Xi with the cost. And then it cannot exceed 14. And so we can call up the solver here. And then, oh, I forgot to reset. So so the objective is the utility, and we want to maximize. And changing variable cells are this X. And then constraints are that total cost cannot exceed 14. And then another constraint is that Xi are binary. So we can choose binary here. Okay, we click OK. And then we can go to solve. So we have the objective of C8, and we want to maximize. And changing variable cells are decision variables. And then the constraints are that the Xi are binary, meaning that it can be either 0 or 1. And then the total cost, C9, cannot exceed 14. And then we click solve. And then the default is simplex LP. So we click solve, and we can see that we actually have the total utility of 43, and total cost is 14. We can try another solver to see. So just remember that our total utility is now 43. So I think I just copy just to keep it, and then I'll just do it again. So I'll just change the solver from simplex LP to GRG nonlinear just to see. And it seems that we get the same total utility. So we can see that the optimal solution selects project 1, item 4, and item 6. So we can go back to say that selected projects are projects 1, 4, and 6, I think. 1, 4, and 6, yeah. And total value is 43. Okay, so this is our solutions. And then the next problem is actually what we have seen earlier, is employee scheduling problem. So so here we have a delivery service company, and then so the company is concerned about labor costs, and then is interested in determining the most effective way to schedule workers. And the hub operates 7 days a week, and the number of packages it handles each day varies from one day to the next. So using historical data on the average number of packages received each day, the manager estimates the number of workers needed to handle the packages as shown in the following table. So based on historical data, so these are like the average number of workers that can handle the number of packages in each day. Okay, so we can see that this is the demand requirement. And then so now we have to consider different type of work shifts. So the package handlers working for Express are unionized and are guaranteed a 5-day work week with 2 consecutive days off. The base wage for the handlers is 6.55 per week. Because most workers prefer to have Saturday and Sunday off, the union has negotiated bonuses of 25 per day for its member who work on these days. The possible shift and salaries for package handlers are given in the following table. So you can see that we have like for 7 type of shifts. So for example, shift one have the Sunday and Monday off, so it start on Tuesday and so on. So the wages for each shift varies based on the holidays, but based on the weekends taken. And the manager wants to keep the total wage expense for the hub as low as possible. With this in mind, how many package handlers should be assigned to each shift if the manager wants to have a sufficient number of workers available each day? Okay, so decision variables are again is xi. So we have xi as a number of workers on um, working on shift I, and we have 7 type of shift. Okay, so we have 7 decision variables, and the model is first we have to find the objective function. So we want to minimize total wages. For example, is 680 x1, because its wage is 680 per person, so x1 is a number of person working on shift I. So we want to minimize all these wages, x2 and so on, until the last one is 655 x7. Okay, so the objective looks like this: mean total wages. And then subject to the constraint is that the number of workers on day I, workers on day J has to be at least required. Number of workers required on day J. And we have 7 days, 1 to 7, Monday to, you can say Sunday to Saturday. Okay, and then another concern is that the xi have to be integer. Xi has to be integer like 1, 2, and so on. Non-negative integers. Okay, so so this is the problem. So we have the objective function of minimize total wages, and then we want to have the number of workers on day J enough to satisfy the minimum required. Okay, and then the decision variable must be non-negative integers. So if we look at our problem, we're going to have like 7 shifts. Okay, so meaning is that so the shift one has Sunday and Monday off, and then the rest they work, and shift two has the Monday and Tuesday off, and so on. Okay, and these are our decision variables. So worker schedule, and then the objective function is this one, objective cell, and then we have to, this is the amount required. This is coming from the manager of the Air Express, and we want to figure out how many staff we have on Sunday. So on Sunday we need 18, and we want to figure out based on these schedules how many people will come on Sunday. So we can see that this is actually this is x1, x2. So this is x2 plus x3 plus x4 plus x5 plus x6. So we can actually do some product of this and that. And then again on Tuesday, so it's x1 plus x4 plus x5 plus x6 and 7. So we can do some product of these two also. So we can actually do the first one and then copy the formulas down. And so now I'm going to call up the solver. So data and then solver. And then I'm going to reset it. So the objective, oh, I forgot. And then the objective is total cost. So we 680 x1 plus 705 x2 and so on. So we want to choose this and we want to minimize, and changing variable cells are all these x's. And then constraint is that this number available has to be at least the number required. Okay. And then we also have the workers has to be integer. So we choose this one, int. And then we click solve. We can change to, yeah, nonlinear. Okay, so now we get the optimum solution of the total cost is this much. And then we can try another solver to see if we can do better. Okay, so I just saved this solution from GRG nonlinear, and I'll solve it again using the simplex LP. And you can see that the total cost is the same, but the schedules looks different. So you can see that total cost is the same. So we have like another type of schedule. So as long as the total cost is the same, it doesn't really matter that much. Sometimes there are more than one optimum solutions. These are called multiple optimum solutions. So we can see that on Sunday we have enough, Monday enough, but Tuesday we have more than enough, and also Wednesday, Thursday, Friday. Okay, so there are 4 days when we have more workers than needed. Okay, so this is a schedule. So you can either pick this schedule like 3 workers on shift 1, 3 workers on shift 2, 6 workers on shift 3, and then no one in shift 4, 7 in shift 5, 2 in shift 6, and then 12 in shift 7. Or you can use